Today we're finishing up our discussion of the acid-base table so we can predict acid-base equilibriums. And specifically we're going to look at, do amphiprotic chemicals act as acids or bases in water? Because remember, amphiprotic chemicals can act as either, so which one's going to be predominant? You'll remember that the direction of any given equilibrium can be determined by looking at the relative position of the acid and the base on the acid-base table. Our acids are on our left-hand side, our bases are on our right-hand side. If the acid is higher than the base on the table, that means that the products will be favored in the reaction. It'll be more of the acid and base neutralizing each other. If the acid is lower than the base, however, the reactants will be favored. There won't be that much reaction. So we can always determine by looking at what our Bronsted-Lowry acid and our Bronsted-Lowry base are, which way the reaction is going to favor. Remember as well, when you do that, you are only looking at the reactant sides. It will get terribly confusing if you look at the product side as well, because then you'll have four things that you're looking at, and it just makes it much more difficult. However, what do we do in the case of an amphiprotic species? If something's amphiprotic, then remember that it can act as both an acid and a base. Well, what we end up doing is we're going to compare the Ka and Kb values of the chemicals involved. So let's take the dihydrogen citrate ion as an example. Dihydrogen citrate is right here. Its formula looks rather complicated. It's C3H5O COOH2 COO-. This is an amphiprotic compound. It can act as an acid and donate away another hydrogen ion to become a hydrogen citrate ion, or it can accept an hydrogen ion and turn back into citric acid. Which one is it going to do? Well, we can actually calculate this. And what we're going to do to figure it out is we're going to compare the Ka value and the Kb value of the species that dihydrogen citrate will turn into. So that means one of the numbers, we just have to look for citric acid. Citric acid has a Ka of 7.4 times 10 to the negative 4. We are going to compare that then to the Kb of hydrogen citrate. Now, when you do this, you're actually going to use citric acid, or the dihydrogen citrate, its Ka value, and use the formula Kw equals Ka times Kb to calculate that. So we can calculate what the Kb for this ion is. Really important thing with this though is this is actually going to be on the table somewhere else. It's right down here. Don't use this number. When you're calculating the Kb for an amphiprotic compound, use the number that is higher on the table. So we'll use the Ka from the conjugate acid, and then we'll calculate the Kb of the conjugate base from the Ka of the species in question. And I'll show you how to do this in the next video as a sample problem.